coming here today. So Mr. Slman will present his thesis. Okay, so inshallah we'll give him 25 minutes from now to finish his presentation. Okay, let's start.
Okay, Assalamu alaikum wa rahmatullahi ta'ala wa barakatuh. My name is Slman Mohammed. And today, inshallah, I will present my MSc thesis work entitled Supervisory PV Battery Grid Energy Management System with Load Shifting Integration for Residential Residual Energy Building. So the thesis is organized into 7 outlines. I will start with introduction, proceed to the methodology. I will present the result in 2 cases. Case 1, primary case and extended case, and we will then conclude and mention the future recommendations. So, based on the definitions by organizations such as US Department of Energy, ASHER, and European Union Energy Performance Building Directive, NetZero energy building is not only a building with renewable energy source, it is highly efficiency building, whereas annual renewable energy generation is offset by the annual renewable energy demand is offset by the annual renewable energy generation. To achieve the balance, the annual renewable generation should approximately be equal to the annual renewable energy demand, and there are some organizations are defining based on the annual export should be higher than or equal to the annual import. In general, there are 2 types of net zero energy building. Grid-connected net zero energy building. In this case, the building will be supplied by the grid and the renewable energy source, and the second type is the off-grid net zero energy building. This one is the islanded one, meaning is that the renewable energy source should be able to supply the building with the energy needed. To achieve the balance, there are 4 types of assessment: site assessment, source, cost, and carbon assessment. So, buildings contribute to around 36% of energy of the global final energy, and this contribute to around 37% of the CO2 emission. Therefore, net zero energy building is important is to reduce this amount. To achieve the concept of net zero energy building, first we need to reduce the energy efficiency in the building by utilizing energy efficiency measure. And second, we need to incorporate renewable energy source to supply the building with the energy needed. And when these renewable energy sources are insufficient or unavailable, we need a second layer, such as energy infrastructure layer, that can provide the building with the energy needed, meaning we need the electrical grid and the energy storage system. To coordinate these 3 layers, we need an intelligent energy management system. In the research focus for the net zero energy building, there are 4 main area of research focus. First is the design stage, and this considers the planning stage. Second is operation and control. Third is economic optimization, and third is resilience and comfort. This thesis focuses mainly on operation and control. Operation simply means assessing hourly assessment of PV generation, a building demand, status of the grid and the battery under time varying condition. Control meaning designing a supervisory energy management controller that can do 3 functions: battery dispatching, grid exchange, and shiftable load operation. So the motivation of this work comes from the temporal mismatch between PV generation and building demand, where the surplus PV time and the evening demand effects arises in the same daily cycle. So this mismatch requires a supervisory energy management system that is capable of coordinating battery dispatching, grid interaction, and shiftable load operation in order to improve self-consumption and reduce unnecessary grid dependency. So, based on this mismatch, the problem is how to operate the net zero energy building while also keeping the battery with impractical constraint and also managing the grid exchange. When the shiftable load is included, the problem becomes how to coordinate the battery operation and also the controllable shiftable load together in order to improve self-consumption and reduce the grid exchange and also avoid excessive battery cycling. This table shows the comparative existing of the related studies all the studies are in the area of operation and control, and you can observe from the table that few of these studies include the three energy management function: battery dispatching, grid exchange, and load shifting. And these studies are mainly based on hierarchical rule-based control, or some of them are based MPC, model predictive control, while physically constrained adaptive fuzzy logic controller for coordinating these functions in hourly horizon remain unexplored. The integration of physically modeled shiftable load, also represented by the heat pump dynamic, is still insufficiently addressed. So my study has three objectives. The first objective is to develop a physically constrained adaptive fuzzy logic controller based energy management system for residential NZEB energy building, account for two: battery dispatching and grid exchange. Second, we need to compare these two supervisory controllers under the same PV load condition and system constraint using battery and grid related KPIs. And the third objective is to model and integrate the thermal shiftable load as a controllable demand side layer in order, and then assess the effect of that on residual PV utilization and grid interaction. So the NetZero energy building plan for my proposed work is annually sized so that the PV generation is approximately equal the building energy demand. Homer Pro is used for sizing the PV and the battery sizing. MATLAB is used for dynamic NetZero energy building plant, and TRNSYS is used for dynamic NetZero energy building, and the supervisory controller is designed inside MATLAB. I use TRNSYS for designing the model because TRNSYS has high capability of designing a real physical dynamic model. MATLAB has the capability of making advanced control. This figure shows the proposed work. The power of the PV and the battery are connected to the DC bus using DC-DC converters, and the DC bus connected to the AC bus using the bidirectional grid-tied inverter, while the shiftable and the non-shiftable load are all connected to the AC bus. The supervisory controller takes measurements from all the components in the proposed system and give two control actions. The first control action goes for battery dispatching, and the second control action goes for serving the shiftable load. So the selected system design in Homer are chosen to support the annual NetZero energy balance with high renewable energy contribution. This table shows the system parameters used in this study. Regarding the PV model, the DC power of the PV is calculated in TRNSYS using Saudi Arabia typical meteorological year weather file, and this TMY file provide hourly data for the solar irradiance, ambient temperature, wind speed, and relative humidity. The building model is modeled in two cases. The first case, the building considers the whole load, and the second case, the load is divided into two in order not to change the initial size of the building. The shiftable load will be result from the heater, electrical consumption, and the pump. The battery is modeled dynamically, not only as a fixed efficiency block, and the SOC of the battery is updated based on the current at each time step. We can observe from equation 8 that the battery voltage is modeled in such a way that it's based on the function of SOC, ambient temperature, internal battery temperature, and initial and internal resistance drop. Both supervisory controllers uses the same constraint layers, SOC and voltage, SOC-based power limits, and no export during discharge. The first supervisory controller is the rule-based controller. In this part, the rule-based controller decision is based on the sign of the mismatch, meaning positive charging, negative discharging. Although rule-based controller is simple, but it is mainly based on threshold value, and this because it does not consider the magnitude of the mismatch, and also it does not consider the SOC condition of the battery. Therefore, I developed adaptive fuzzy logic controller to solve this issue. The adaptive fuzzy logic controller is is adaptive input conditioning. For this, the adaptive fuzzy uses two input. The first is the power mismatch, and the second, the first is the power mismatch, and this tells us where there is defect or surplus. The SOC tells us the condition of the battery. The deadband is used in order to ignore very tiny mismatch, and the scaling factor is utilized to scale the to scale the mismatch for normalization. Then the mismatch is normalized between 1 and -1 for fuzzy input ranges. The second state is a fuzzy state, and in this case, the input and the output are fuzzified, as we can see from the figure. After that, the rule-based table is used for inference, and the final crisp output is calculated using centroid. For the third stage is adaptive output conditioning. For this case, the power mismatch factor is used to adjust the command of the command based on the mismatch magnitude. Then the SOC factor is utilized in order to adjust the command based on the battery condition. And the adaptive ceiling is then used to maximize the allowable battery command. And finally, the final command will be result from multiplying the normalized fuzzy output by the adaptive power ceiling. And this final battery command will be filterized using alpha. This table shows the system, the controller parameters used in this study. Regarding the shiftable load control logic, it is mainly based on the surplus of the PV after charging the battery. The condition for activating this shiftable load, first, there should be a permission window, meaning the time zone which is specified the maximum PV surplus. The second, there should be a request for that shiftable load, and third, the surplus PV should be higher than the power shift margin in order not to aggressively switch on the shiftable load. And finally, when the surplus PV power is not enough to provide the load, the shiftable load, with the power needed, the grid will take place. These conditions simply reveals what happened inside these equations, and this figure shows that the controller will check the difference between the reference request and the actual heat pump electrical power, and then send command to the thermal shiftable branch. Regarding the export and import part, they are calculated differently. For the first case, the power export and import are based on the PV power, the load power, and the power of charging and discharging. And if the mismatch is positive charging, negative discharging. The second case, the same account is happened, but the export and import will happen after serving the shiftable load. This figure simply reveals how the co-simulation between TRNSYS and MATLAB happen. TRNSYS has a dynamic model, meaning is that it's sending the measurement signal for the PV, the non-shiftable load, the battery status and the SOC of the battery, the shift request, and the permission window, all will be sent through type 155 interface to MATLAB. MATLAB, on the other hand, sent two control actions. The first for the battery dispatch, and the second one for serving the shiftable load, while the grid export and import will be a consequence of the power balance equation. This figure simply shows how the simulation done, and the colors shows the flow signal inside the model. The table in the left shows that, or reveals that for every component in TRNSYS there is an equivalent type name. To assess the building, I used two KPIs, battery and grid related KPIs. For the first case, the simulation uses a representative 1 week, 168 hours, and one time step. The load delivery is 4.6 kilowatt and the PV capacity is 16. The main objective of the first case is to identify which supervisory controller provides the better trade-off between grid performance and battery-friendly operation. This figure shows the battery power and the battery current response. We can observe that the rule-based controller follows the mismatch more deeply by the blue color, and it also produces sharp charging and discharging. The adaptive physiology controller by the rate provide more graded response because it considers both the mismatch and the SOC. This for the current, and you can see that the rule base provide large current variation and strong electrical stress, while adaptive physiology controller provide reduces the root mean square current and the abrupt command variation. This figure is for battery voltage and SOC of the battery. You can observe that the rule-based controller charge the battery deeply while maintain higher SOC, while adaptive physiology controller maintain higher minimum SOC value, and this give like more battery aware operation. Regarding the voltage drop, the voltage variation, the rule-based controller, the adaptive physiology controller reduces the voltage swing from 12.8 until 7.2, and this means that indicate smoother voltage and lower electrical stress. This figure is for export and import. Rule-based controller give lower grid import, but this is because of the strong charge and discharge, while the adaptive physiology controller give lower peak and improve battery friendly. This figure simply explains that both controllers and net export, and these tables reveals the information regarding evaluating the battery related and grid related KPIs, which indicates that adaptive physiology controller give better battery KPIs while also maintain reasonable or acceptable grid KPIs. These figures, I just changed the rule-based table in order to check the sensitivity analysis of the adaptive physiology controller. I checked 3 cases. The first, conservative case, and for the conservative case, it reduces the charge and discharging around the near SOC limit, and this give us like better battery protection, but give very weak participation. And the figure in the left shows the normalized fuzzy, and figure in the right shows the actual battery board command. This is for the balanced selected case. It gives like useful SOC range action, and also give better compromise between battery participation and battery aware operation. And this is the last case for the aggressive. It aggressively charge and discharge the battery, and this gives us like higher range of SOC. It gives us for sure good participation, but also this is increase the battery cycling and stress. These 3 figures for battery power, voltage and SOC and grid power for these 3 selected cases, we can clearly see that like the conservative case shows lower battery participation and minimum SOC voltage variation, but this provides lower grid participation during BB defects, while the balance, which is the selected one, provide moderate battery participation and keep the SOC and voltage response more stable and provide best compromise in grid power support. And the aggressive case give us like strong battery participation, but causes deeper SOC and high voltage variation, and this provide higher grid participation, higher grid participation with more battery friendly operation. This figure shows the representative one day in summer and 1 day in winter. We can observe that from in the winter time there is high surplus PV power, meaning it will be used to feed the load. The rest will charge the battery. After charging the battery, the remaining will be exported. This is in the surplus time. In the defect time, when there is no PV power, the battery will discharge to the load and the remaining will be covered by the grid. The same cycle happens for the winter day, and we can observe the difference between the two, that in the summer day, there is more export by the yellow color more than in the winter day. The second case is for, or the extended case. The objective here is to assess the effect of adding shiftable load, shiftable Slman load on residual PV utilization and total grid exchange. The figure A shows the residual PV utilization, meaning is that is the surplus PV power. When there is remaining after shelving the shiftable load, it will be exported to the grid. And this figure shows the shiftable load supply allocation, meaning the shiftable load will be supplied from both. First, the PV will cover the whole, most of the shiftable load. When there is very small time defect, it will be covered by the grid. This figure is for the thermal loop part, and the figure in the left shows the requested power is accurately tracks the heater pump output, the actual heater pump output, and this is the internally how the shiftable load will be changed based on the water tank flow rate and the SOC and the temperature of the tank. This table compare between the battery board in the first case and the second case. The first case was using the whole building load, but in the second case the load is divided into two, shiftable and non-shiftable load, meaning is that the battery in the second case will be able to see only the shiftable load. So for this, the battery KPIs has clearly improved battery throughput and battery throughput RMS, and also the peak discharge power for the battery. And you can see the battery voltage and SOC are more stable, and the only affected one is the discharge is became more stable also. So this figure is for like checking the shiftable load impact on power export and import. Meaning, after adding the shiftable load, the grid KPIs have clearly improved. This can be seen from the figure and from the table. This figure simply shows that in both before and after adding shiftable load, the building is still net export. The import, export, and total exchange also have been improved when adding the shiftable load. After revealing the information about daily and weekly profile, this is tell us the information about how yearly the building is performing. We can observe from the table and the figures that the grid import, the total grid exchange, and the self-sufficiency have clearly improved, while only the grid export is improved by 0.57%. So, to conclude, a physically constrained adaptive fuzzy logic controller based energy management system was developed for residential and NZEB energy building, and the adaptive fuzzy improved battery aware operation by reducing battery throughput, RMS and SOC excursion, while also maintaining acceptable grid performance. The load shifting improves the residual PV utilization and also reduces the grid interaction. For the future work, economic study for tariff analysis for export and import can be studied. Also the scalability, meaning that community scale NZEB energy building instead of like single NZEB energy building, electric vehicle heat pumps, hydrogen storage, and maybe checking another like kind of controllable load can be done. So these are the references that I have utilized in this presentation, and these are the conference publications for 10 projects. And for the thesis part, the thesis, I'm targeting 3 papers from the thesis. First one is published as a review paper in Q1 Journal Energy and Building, and the second one is now ready to be submitted. The third one, inshallah, I'm still working on. So before I finish, I would first need to thank the Kingdom, KFUPM, and the department for giving me this opportunity to become a part of this repeated university. And second, I would extend my gratitude to my advisor, Dr. MD Shafiullah, and because he's a really special person. He really helped me during the research part, and he also gave me the opportunity to participate in the Jubel project, and he's the one who came up with the idea of NetZero energy building. Second, I will extend my gratitude to Prof. Mohammed Abidu and also Dr. Nizar Al-Lizidi for their guidance and support and their knowledge. Third, I need to extend my gratitude to Dr. Mohammed Al-Qadim for his guidance, support also, and his, mashallah, knowledge. And I need to extend my gratitude to Mr. Hussein, the guy who helped me when I started using TRNSYS. And I need also to extend for the acknowledgement for my family, because I think they are watching now from there. And also I need to first thank those first two people, Mazin and Muhammad Umar. MashaAllah, they are educationally gifted people. When we came together here in the university, and we taken all the courses together, MashaAllah, and they helped me, even we participated in all the conference publications, alhamdulillah, with those two amazing people. Thank you so much. Can't thank you enough. Second, I need to extend my thanks to Sheikhna, Sheikh Khadir. MashaAllah, Sheikh Khadir is one of the knowledgeable people in the department. MashaAllah, tabarakallah. Third, for Dr. Khalil. Khalil is now the new president of Sudanese community. And extend my gratitude also to the group research. Thank you so much all. And then I will extend my gratitude for Phase Control and poor people and Sudanese community at all. If you did not see your picture here, but I did not find a time to cover all the pictures. I'm so sorry for that. And gratitude also to Mr. Mohammed Tijani and my roommate for the arguments and discussions, political discussions. Thank you so much, Mr. Tariq, and wish you that you can find what you look for. And thank you so much.